let's go ahead and try an example of this percent efficiency equation. Let's go ahead and start super simple. Let's start with just an inclined plane. And let's say this inclined plane is just 2 feet tall. And then let's say the span of this ramp is 20 feet long. And let's say we're trying to push up some 50-pound force. And that would, of course, be our force resistance. And let's make this just a weight, a shape, a box, let's say. And let's say some dude, or dudette, I guess, could be pushing up this box, up this ramp. There's no reason why a dudette couldn't do it. And let's say he has to apply a force effort of 6.5 pounds to get it up the ramp. And that's because of friction. The friction in the system, the friction pushing this box up this ramp, adds to the force required that wouldn't be required if we were dealing in theory or in our perfect world or our ideal world. So because of this extra force we have to apply to get this box up the system, let's ask the question, what is our percent efficiency? And so to solve, we're going to use this equation up here. We need our AMA and our IMA. So let's start with our AMA. Well, that is our AMA-free equation, which is FR over FE. And we know these numbers, luckily. And our FR is, of course, 50 pounds over here. So 50 divided by our force effort, which is 6.5 pounds. And then I don't really know what that is, so we'll type it in our handy-dandy calculator, and we get 50 divided by 6.5. Oops. 6.5 pounds. And what do we get? We get 7.6923. And so we'll go ahead and we'll cancel out pounds, because pounds cancel out. And we'll just write it as 7.69 for our actual mechanical advantage. And then we can solve for our IMA, which is just our IMA-DER equation. Our IMA equals dE over dr. And we know both of these numbers as well. We know that our dE is our distance efforts traveled, which is just 20 feet. And then we know our distance resistance is the height of the inclined plane, is just 2 feet, and that's pretty simple. We really don't even need a calculator to solve this. Feet cancels out. 20 divided by 2 is 10. And at first glance, that might seem kind of weird to get these different mechanical advantages. But really, the reason why we do is because, like we said, our AMA is always smaller than our IMA because we added that effort force. We added to our effort force by adding friction to the system. And we really didn't actually add friction to the system. There's just friction in the system when we're dealing with the real world. And that's kind of the point of percent efficiency. We're trying to calculate how much energy we lose to things like friction. And it's lost to other things, as we said, besides friction. But let's just keep it simple. Let's just say that friction is the main driving force. But we go ahead and put our AMA on top and our IMA on bottom. And then, of course, we multiply that by 100. And to figure this out, we'll pull out our handy-dandy calculator. And what's really cool about this calculator is we can open our parentheses and then hit this button right here, this numerator over denominator button. And we sort of get this sort of fraction style. And we can type in 7.69 on top. And we can put 10 on bottom like it is. Then we can leave it or close our parentheses and just write 100. And you can see we actually wrote it out exactly as it's written here. We just hit enter. And we get a percentage of 76.9. And you might have been able to do that in your head because it's a system of 10 and 100, and you just move the decimal place over and over again.
But we get a percent efficiency
of 76.9%. And that's our final answer. And what does that mean? What does 76.9% mean? It means because of friction in the system, we've lost almost a quarter of our energy, or we've lost almost 25% of our effort because of the friction fighting back in the system. And you might say, Mr. Anderson, can we just grease this ramp down or add wheels to get rid of that friction? You'll get rid of some of it, but you can never get rid of all friction. So doing something like adding wheels, you would actually increase the efficiency to some higher number, higher than 76.9, but you will never get to a full 100% efficient system. And that's kind of the point here. So if you ever are solving for percent efficiency and you get 100 or even higher than 100%, you know you've done something wrong and you need to go back and figure out what that is. Getting a percent efficiency of 100% is breaking the laws of physics, and you're not allowed to break the laws of physics in my classroom. The same goes for getting an efficiency higher than 100%. Remember that.